title on the slide and what's in. Can you hear me? All right. So those who actually read the program might have noticed that the title on the slide doesn't match what's in the program. I've been kind of going between several titles for the talk and the paper, and I wanted to highlight chromatin state in the title because, well, we're trying to discuss to discuss intron retention and put it in the context of chromatin state. So intron retention, splicing, what does that have to do with chromatin? Well, we by now know that splicing is co-transcriptional, so chromatin state can and does affect splicing outcome. So what we're going to try and do is to predict on the basis of sequence whether an intron is going to be retained. And specifically, we're going to only focus on subregions within introns that are DNA accessible. And we had a paper last year where we showed that, yeah, we can, using deep learning, distinguish between hypersensitive sites that are part of a retained intron and those that are not. And what this paper also showed is that transcription factors rather than splicing factors were probably the most important contributors to this process. And so what we did in the meantime was to kind of dig in a little deeper and try to find what we can do with other deep learning approaches other than that simple three-layer convolutional network that we used in our original work. And well, we've been hearing a lot about DNA large language models, and we know that their representations are useful for various regulatory genomics tasks, but the question is, well, how do these do for our task? Well, we're also going to try something else, and that is to use chromatin state models. So what I mean by chromatin state models are models that map sequence to a whole collection of variables that describe chromatin state, like DNA accessibility, transcription factor binding, histone mark, etc. So you all probably know some of these models that I've listed up there. And in this work, we're specifically going to use the SAY model, which maps from a 4 KB sequence to a set of 21,907 different chromatin profiles, almost half of which represent transcription factor binding propensities. So the idea is to leverage the representation learned by SAY to try and predict retained introns. And so what we're seeing in these ROC and precision recall curves is that the fine-tuned SAY model, whose architecture is shown in that figure, that model performs better than a Basenji-like model or a simplified version thereof, which both perform better than using the representations generated by DNA BERT2, where for the DNA BERT2, we used a similar architecture to what we used for SAY. And so, okay, that's good news. Well, the next thing we tried is something even simpler, and that is to just use logistic regression over the transcription factor targets produced by SAY. So we take our sequence, we map it to the list of transcription factor or DNA binding protein binding propensities for that hypersensitive site, and then feed that 9,000 some dimensional representation to a logistic regression model. And lo and behold, that performs almost as well as the fine-tuned SAY model. And well, since we have logistic regression, that gives us easy interpretability. So these are the top 20 weights from the logistic regression model. And the first thing we see are targets related to RNA polymerase. And as we know, the rate of elongation of the POL2 has an impact on splicing. And so that's good that our model picked up on that. There's also AFF4, which is involved in regulating polymerase transcription elongation. So that is another positive case. And the next is MYC, which is a well-known oncogene that also does its work by probably by affecting intron retention. It is known to regulate alternative splicing. There's also everybody's favorite protein, CTCF, which also is known to be involved in alternative splicing. So 9 out of the top 20 are already known to be somehow involved in alternative splicing. So probably some of those other top 20 are worth following up on. So in conclusion, the chromatin state model provided better accuracy than a DNA large language model. And I don't know if Peter Koo is in the audience. He has a recent preprint where they came to similar conclusions on several additional tasks. And probably there needs to be some biological follow-up on the transcription factor connections that we have found. So with that, I'll thank the students who did the work, and there's a link to a bioRxiv preprint for this work. Thank you.
Thank you very much. We have time for one question, I think.
That was cool. Thank you. Larry Hunter, I don't know if he's in the room, but he told me yesterday about this technique called influence analysis from the 60s, which I had not heard about. But it strikes me that you could do this because you're using logistic regression. Not only could you identify the important features, but you could identify the important examples from your training data that are most influential. And so that might be something else to look into.
All right. Thanks, Bill.